Hi, welcome back. So in this video, we're going to be covering another problem, problem 5 actually, which is called the maximum length of pair chain. So let us see what the problem asks. So the problem statement is as follows. You're given n pairs of numbers, and in every pair, the first number is always smaller than the second number. Now we define a pair CD can follow another pair AB if and only if B is less than C. Chain of pairs can be formed in this fashion. So you're given a set of pairs and you're supposed to find the length of the longest chain which can be formed. You needn't use up all the given pairs and you can select the pairs in any order. So let's take an example just to understand what this is talking about. So we're given a bunch of pairs. So in this case, we have 1, 2, 2, 3, and 3, 4. And we're supposed to output the longest chain that we can form in these pairs. So a possible longest chain here is of length 2, and it is 1, 2, 3, 4. Now the reason this can form a chain is because 2 here, this number, is less than 3. So here it says we define a pair can follow another pair if and only if B is less than C. So here this is A, right? This is B, this is C, and this is D. So here B is less than C, so we can say that this follows each other. So we want to find the longest chain that we can form from a lot of pairs that we're given. So let us have a look at the solution. We will do a recursive solution, and first of all, we want to note a few things. First, note that if AB is before CD, then A is less than B is less than C less than D. So A is less than B because in the question it says A is always going to be less than B, and it also says C is going to always be less than D, right? Because it's a pair. So these two inequalities are explained. But what about B is less than C? Well, if the elements are in a chain, then we just said that we need B to be less than C. So we need this inequality too. So that's the first thing that we notice. So for example here, 1, 2, 3, 4, we have 1 is less than 2 is less than 3 is less than 4. So an idea that we should get is to sort all the pairs based on the X point and then on the Y point, so that we have them ordered in that way so that they can form chains. Then after we sort all the pairs, we define Ri as the longest chain from pair 1 to pair I in the ordered way. So there's two cases here. Either the longest chain ends at pair I, or the longest chain doesn't end in pair I. So for 1, then R is equal to maximum of 1 plus RA, 1 plus RB, 1 plus RC, where A, B, C fit the ith pair. Now what does this mean? So let's think about the ith pair here, right? So the ith pair here is 2 elements, right? And it's here. And then there's the I minus 1 element here, right? And then there's a lot of elements here all the way down to the first element, which is here, right? Now, we're saying that Ri, if the longest chain from pair 1 to pair I ends here, then the chain is from some element here jumping to the ith one, right? So there's an element here that fits I, that goes well, that I follows it, and so that's why we say, okay, this element might be A. Another element in the middle here might be B. Another element in the middle might be C, and so on. So in the middle, there's a lot of elements which would fit I. So we say Ri, the longest chain from pair 1 to pair I, if it ends in pair I, then it's going to be 1. So 1, which is this element, plus the longest chain from pair 1 to pair A, or from pair 1 to pair B, or from pair 1 to pair C, and so on. So if we start at the ith pair, and we go back all the way to the first pair, and we check for each pair of them. We check if it fits, if it goes well, if it follows this inequality with the ith pair. Then we add it into this maximum function, 1 plus RA. So A, B, C, D, E, all of them fit the ith pair. Now what about the case when the longest chain doesn't end in pair I? So that means simply Ri is Ri minus 1. The longest chain should be here. So we combine this and we get a recurrence for all the cases, which is Ri's maximum of Ri minus 1, so this one comes from here, or 1 plus Ra, 1 plus Rb, and this one again comes from here. So that's the combined recurrence for all the cases. Of course, here the base cases are 1 equal 1, because if we have only one pair, the longest chain is simply this element. It has length 1. So let us have a look at the dynamic programming solution. So it does work, but it's exponential. So we're like, if we only follow the recursive way, it's actually exponential. So it does work, but it's exponential. It runs at exponential time. So that's why we're going to be using dynamic programming to store the values of the recursions and take it down from exponential to polynomial time. So we set R0 to n1 to be an empty array of size n. And we're going to sort all the pairs. Now this operation, if you're familiar with sorting algorithms, this operation can take O(n) log n time, right? So this takes O(n) log n times. Excuse me for my handwriting. So O(n) log n time. And then we set R0 equal 1. That's the base case, right? And then we go for I equal 1 to n minus 1. Ri is equal to Ri minus 1. So that's the first part of the recursion, of the recurrence relation. And then we go for j equals 0 to I minus 1. If pairs j, so if the pair, so we're at pair I here, right? So we're going from j, from 0 all the way to I minus 1. So I'm checking if pairs j, if this pair, second element here, is less than pairs I, first element. So it's smaller than the first element. Then I set Ri is equal to maximum of its current value and Rj plus 1. So Rj plus 1 here, because j fits with I, so I can set it to Ri's maximum of both of them. And then I repeat this for j equal 1, 0, 1, 2, all the way to I minus 1. And finally, I return our solution that we want, Rn minus 1. So this solution should take O of n squared time, because we have two loops, and so two loops, and each of them might go from 0 to n, so that's an O(n) squared solution. So here's the dynamic programming code. So we're first including IOStream, vector, and algorithm. So if you didn't know, C++ already offers a sorting algorithm in the algorithm directive. So all you need to do is just include algorithm, and you're good to go. Now, so we're gonna call the function. We're gonna write a function called find longest chain, which takes a vector of vectors. So it's gonna take the vector of vectors. So the inside vector is going to be just a pair. Like here, it's 1, 2, 2, 3, 3, 4, right? and then we do a vector which is called pairs, and it has all these pairs, right? And we call the find the longest chain on pairs. So we give the pairs to the function, and first of all we set up an array called DP, dynamic programming, and we set its size to be pairs.size. So pairs.size is how many elements are there in the vector, which is n elements. Now we sort. So this sort function comes from algorithm. We don't need to write a sort function. So we just write sort pairs.begin pairs.end. These are iterators. If you don't really need to know what they are right now, but they're basically used when you're using these kind of functions, which are used in the C++ standard library. So you just sort the elements pairs.begin pairs.end, and they get sorted into ascending order, which is what we want. Then we set dp0 equal to 1, and we go for int I equal 1, I less than pairs.size, which is I less than n, plus I, dpi is equal to dpi minus 1, and then we go for int j equal I minus 1 to 0. We do if pairs j1, so that's the second element, is less than pairs I0, so that's I first element. Then we do dpi is equal to the maximum of dpi and dpj plus 1, so the current value and dpj plus 1, and finally we return dpn minus 1, and n here is pairs.size. So pairs.size here is like 3. So when we run this, we indeed get the answer, which is 2. And this is basically this process takes O of n log n, as we mentioned. So this one is O log n, and this process takes O(n) squared. We can actually take this down. So we can take this down into a log n approach instead of O(n). So we can take these loops and change them to an O(n) log n solution, like this one. But it's a bit more advanced than what this course should offer. But just know that the optimum solution for this problem is actually O(n) log n. You can solve this problem in O(n) log n instead of O(n) squared here, because the sorting is done in O(n) log n, and these two loops are right now they're O(n) squared. So the whole solution should be O(n) squared, right? But you could actually manipulate the inner loop here and make it use a method like binary search to take down the solution from O(n) times n and you take it down to O(n) times log n, which is O(n) log n, and your solution ends up being total of O(n) log n plus O(n) log n, which is O(n) log n. So yeah, just know for now that the optimum solution is actually O(n) log n, but for now our solution, this function here, is actually O(n) squared, and it's much easier to code and to understand. So yeah, hopefully you understood how the dynamic programming plays here, and you see how the recursive solution would have been exponential, like we explained in other examples before. And again, dynamic programming took it down from an exponential solution all the way down to polynomial solution. So I hope you enjoyed the video, and I'll see you in the next video.